will continue with solving problems related to work done and heat transfer, and we will start with a problem which is displayed in the screen. So, this problem is little bit advanced as compared to some of the previous problems where we had only one spring. Now, here you have two springs with the same spring constant are installed in a massless piston cylinder arrangement. So, there is the piston has negligible mass and the outside air is 100 kilopascal. If the piston is at the bottom, both springs are relaxed and the second spring comes in contact with the piston at 2 meter cube volume. The cylinder contains ammonia initially at minus 2 degree centigrade, quality equal to 0.13 and volume is equal to 1 meter cube, which is then heated until the pressure reaches 1200 kilopascal. At what pressure will the piston touch the second spring? Find the final temperature and the total work done. So, let us go through this problem carefully. So, both the springs have spring constant K, mass of the piston is 0, P0 is 100 kilopascal. So, whatever data is given, what we will try to do is that based on the given data we will try to plot PV diagram for the process. So, let us so the first thing is given that if the piston is at the bottom, this is a hypothetical, if the piston is at the bottom, not really that it is actually at the bottom. If the piston is at the bottom means if the volume is 0, then both the springs are relaxed, that means there is no spring force and therefore pressure will be equal to P0. So, this is again a hypothetical point. The hypothetical point, so you may argue that when the volume is 0 then how do you have a pressure? See, you have no fluid inside. So, here you have to consider a limiting volume V which is tending to 0 because the piston is just at the bottom, some limiting volume is there. For that limiting volume there is an inside pressure which is balanced by P0 because both the springs are relaxed and the weight of the piston is also 0. So, what balances at that relaxed condition is only the atmospheric pressure. So, it helps you only to plot the data from an hypothetical given condition, not that it is a real physical state. So, but this is not the real situation. Now, here the process takes place through heat transfer and the piston goes up. When the piston goes up, there is a particular point when the piston is in contact with both the springs. So, the first point is the state point 1 at which it starts. So, state point 1, at state point 1 the system is ammonia, so from ammonia table, just like water property table you have ammonia property table, at minus 2 degree centigrade, which is the initial state, you get what is Vf and what is Vg. This is from saturated table. So, then V1 is equal to x1 Vg 1 plus 1 minus x1 Vf1. This we learned in properties of pure substances. So, from this Vf, Vg and what is x1? x1 is 0.13, this is given. So, you can calculate what is V1. Okay. So, you can get, so total volume at state 1 it is given, that is 1 meter cube. So, small V1 will give you what is the mass. So, state 1, what is P1? Because it is in the two phase region, P1 is the saturation pressure corresponding to Psat at minus 2 degree centigrade. So, state point 1 we know P1 V1. So, once you know the state point 1, then you know actually the locus, which will be this straight line, which will continue up to the point when this piston touches both the springs, because when it touches both the springs the restoring force will double. Earlier the restoring force was related to this spring only, but when it touches this spring also the restoring force will double, and because the restoring force will double, the slope of the PV diagram will also double. So, this point 2 we do not know, but wherever this point 2 is, from here the slope of the PV diagram will double. And state 3, the pressure is 1200 kilopascal. So, the actual PV diagram is something like this. But this point 2 is not known. So, a part of this problem is that what is the pressure at this point 2. What is known is what is the volume at point 2, because it is given that at this point the volume is 2 meter cube, at which the other spring also touches the piston. Okay. So, now because both the springs have same spring constant, so we can write this is state point 3, P3 minus P2 by V3 minus V2 is equal to 2 into P2 minus P1 by V2 minus V1, right. So, now from this hypothetical data point you can calculate this. How you can calculate this? The point 0, 1, 2 are parts of the same straight line. So, P2 minus P0 by P1 minus P0 is equal to V2 minus V0 by V1 minus V0. Just like y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1, the equation of a straight line. That is what we are doing here. So, V0 is 0, V1 and V2 are given. So, from here you can calculate what is P2. That P2 if you substitute here, you will get what is P3, right. P3 is already sorry, V3. This is P3 is given. So, from here you can calculate what is V3. So, P3 is given, P2 you have got from here. So, this is known, V2 is known, V2 known, V1 known, P1 known. So, from here you will get what is V3. So, then let me give you the answer to the first part. This P2 is 694.875 kilopascal. Okay. So, then the question is what is the final temperature and the total work done. So, final temperature is what? Final temperature you have to identify state 3 from the table. So, one data point is given as P3 is equal to 1200 kilopascal. The other data point is V3 is equal to this one. So, this combination will give you state 3 from the table. So, state 3 means what is T3 from these two data. So, that T3 is 51 degree centigrade. And what is the total work done? So, W12 this is again a trapezium area under this. So, half into P1 plus P2 into V2 minus V1 plus half into P2 plus P3 into V3 minus V2. So, if you substitute all the values, this will be 1342.6 kilojoule. Okay. So, we will work out another problem from this chapter heat and work. let me erase the board before we come to that problem. So, that problem is problem 2.6, which is displayed in the screen. So, you have a cylinder with area of cross section as 7.012 centimeter square, has 2 pistons. The upper piston, which is given as P1 in the diagram, has a mass of 100 kg. It initially rests on the stops. The lower piston has a mass of 0 kg, that means it is effectively massless, has 2 kg of water below it with a spring in vacuum. So, the medium in which the spring is there is in vacuum, there is no pressure from that medium. The spring force is 0 when the lower piston stands at the bottom, again it is a hypothetical state, and when the lower piston hits the stops, the volume is 0.3 meter cube. The water initially at 50 kilopascal and 0.00206 meter cube is heated to saturated vapor. Find the initial temperature and pressure that will lift the upper piston, and final temperature, pressure, specific volume and work done. So, it is a very comprehensive problem. We will look into this problem in some details. So, here is water, then there is a spring, then there is another piston. So, 2 pistons, and the upper piston is initially resting on the stops. We will try to understand the process by drawing PV diagram. So, I am just preparing it to plot the pressure versus volume. Now, first of all, so here there is vacuum. First of all, you tell me one thing, what is the system here? So, the system here is nothing but this water, and we are drawing the PV diagram for this system. So, let us see what is there, what is given. So, what is given is that the spring force is 0 when the lower piston is at the bottom. Okay. So, what is the resistance force due to pressure here, which is 0 because it is vacuum, due to spring force plus due to the weight of the piston. This piston has weight negligible. So, only force that it is encountering when this is at the hypothetical bottom state is the spring force, which is 0, that is given. Then, so this is one end of the spectrum. The other end of the spectrum is that when heat is transferred to it, this piston alone starts moving before it encounters a situation when this piston is also lifted and they move together. So, let us identify that condition when these 2 pistons move together. So, when the 2 pistons move together, So, the free body diagram will look something like this. This is a very interesting situation because they are moving together. See, this spring force is like internal action reaction force, it contributes to nothing. So, as if these two pistons together is moving like a single unit. So, you have this P0 into A PA and MP1 G, right, MP2 is 0. So, P into A is equal to P0 into A plus MP1 G. So, P is equal to P0 plus MP1 G. This P we say equal to P lift, where by P lift what we mean? By P lift we do not mean that when this is lifted, by P lift we mean that when both of these pistons are lifted together. So, this P lift, if you calculate it, it is 1500 kilopascal. So, now let us try to draw the PV diagram. So, this is a two phase region. The P lift, this is 1500 kilopascal, say so then we have to figure out that what is the state, what is the volume here which will lie on this line, what is the volume at which both the pistons move together and then they will follow this line. Okay. So, up to this it will be a linear variation because the spring is a linear spring and there is a state point 1 which is lying on that. Okay. So, state point 1 it is given state 1 P1 is 50 kilopascal and V1 is 0.00103 meter cube per kg. So, let us calculate, let us consider, let us say that this is state 1A. So, up to this there will be a straight line and we can write the equation of the straight line as follows: P1A minus P1 by P1A minus P0 is equal to V1A minus V1 by V1A minus V0, right. So, P0 is 0, this is equation of the straight line. V1 is V0 is 0, P1A is P lift, P1 is given, V1A we do not know, V1 we know, then P1A is P lift. So, from here you can calculate what is V1A. So, if you calculate it, so you can write also it in terms of the specific volume V1A, you will find that after calculation this is less than V stop. V stop means that is 0.3 meter cube by 2 kg, that is the V stop. So, this is less than V stop. So, where is the V stop? Let us see what is Vg at here. So, V stop, which is 0.15 meter cube per kg. If you look into this 1500 kilopascal data, then you will see that this V stop, this is less than Vg at 1500, sorry, this is greater than Vg at 1500 kilopascal. It is not visible, huh? Okay. So, I will write it at a separate place. So, V stop, whatever is calculated, it is greater than Vg at 1500 kilopascal. So, V stop is physically here, whatever small v or capital V depending on, in this case you are drawing a small v diagram. So, what it says is that it is heated to saturated vapor, that means these two cylinders will go together, but the lower cylinder will not hit the stops, because had the lower cylinder hit the stops it has to go beyond this, but the process will stop when it becomes saturated vapor, that is what is given. So, from 1A to 2 it will continue, but the lower cylinder will not the lower piston will not hit the stops. So, the PV diagram is from 1 to 1A and then from 1A to 2. So, based on this the initial all the problems, all the parameters for the problem can be obtained. So, first is initial temperature. So, from P1 V1 from table you will get what is T1, table means water table. So, T1 is 81.33 degrees centigrade. Okay. Then the final temperature, pressure and volume. So, state 2 you have V2 as Vg at 1500 kilopascal, T2 as Tsat at 1500 kilopascal, and pressure is already 1500 kilopascal. What is the work done? Okay. So, this the first part of the work done is the area under this trapezium, the second part is the area under this rectangle. So, this is the area under the trapezium, this is the area under the rectangle, all these are known. So, per unit so the total work done will be 348.91 kilojoule. So, again the problems which we have worked today, we wanted to illustrate through this that by visualizing the problem through a proper PV diagram, it is very convenient to calculate the work done. So, instead of just hypothetically trying based on the initial state and the final state, you draw the processes and then integrate PDV to get the work done. Thank you very much. We will continue in the next lecture.